What are acids, bases, and salts? In ancient times, they could tell the difference between acids, bases, and salt by tasting it. Of course, we don't do that in our chemistry laboratory, but in general, acids taste sour, bases are bitter, and salts are salty. How do they feel? If you get acid on your skin, it stings. A base, however, when you go to rinse it off your skin, it's slippery, and that is because the base dissolves the fats in your skin. Acids and bases can be both harmful to your skin in different ways. So whenever you get any of these substances on your skin, you want to remember dilution is the solution. So go over to the sink and rinse it off with lots of water. Acids and bases and salts all react with metals. Generally a very strong reaction with most acids. Bases is a weaker reaction, and salt is pretty strong. Electrical conductivity, they all conduct, and that is because they produce ions in water, and if there are ions in an aqueous solution, then they can carry a current. We will talk about later on strong acids and strong bases and weak acids and weak bases. Electrical conductivity is associated with that. If you have a strong acid or base, then it is a strong electrolyte. If it is weak, then it is a weak electrolyte. And salts are always considered strong. Indicators. If you have litmus paper, then acids turn blue litmus paper red and bases turn red litmus paper blue. I always remember for bases, bitter blue bases. And then salts can be neutral, but they can also be acidic or basic. In the pH scale, 7 is neutral, so right in the middle. Some salts, they are neutral. Your acids are always going to be less than 7. Your bases are always going to be greater than 7. Hydrochloric acid is a very typical acid that we use in the chemistry classroom. Bases, sodium hydroxide is a very typical chemical, and sodium chloride is table salt. A lot of industrial uses with acids, and with bases they are used to make soap. Salts, you might see them in a medical setting in saline solution. We are going to be working with organic acids in this unit. In an organic acid, it has a carbon backbone, and then it has a carboxyl group. And so it looks like this. What makes it acid is this hydrogen can come off in solution and produce a hydrogen ion. And so that is our acidic particle. The very smallest organic acid is formic acid. And it does have a particular smell. If you've ever stepped on ants and smelled the result of that, it's have this formic acid in it. So it just consists of one carbon for formic acid, and then this is a little H group that can come off. So be careful. Sometimes they rate it like this with a COOH, and it's not a base. So even though it has that little OH group off on the side, that little H is what comes off to form the acidic particle. In general, reactions with acids and bases, AP chemistry doesn't require you to predict products, but this is some of the reactions that you might see when acids and bases react. So acids react with metals to form hydrogen gas. Not all metals will do this, but this is a very typical reaction. If there is a gas formed when a metal is added to an acid, then hydrogen gas is usually what is the gas. Acids react with carbonates and hydrogen carbonates to form carbon dioxide, so the bubbling would be due to carbon dioxide. Hydrogen carbonate, that is found in baking soda. Baking soda is sodium hydrogen carbonate. So when we add baking soda to our food, it reacts with the acids in the food and produces carbon dioxide gas, and so that is the little gas holes that you might find in your baked goods like your muffin or your banana bread. Bases and acids, when they react, they will do a neutralization reaction and make water and then a salt. Bases also can react, and when they react with metal ions, they can form precipitates. Bases reacting with hydrogen carbonate, again, you would get carbon dioxide gas. And again, bases reacting with the acid, you would get a neutralization reaction, water and a salt. Some common acids and bases, so HCl, hydrochloric acid, H2SO4, sulfuric acid. Common bases, NaOH, sodium hydroxide or lye. Magnesium hydroxide, that's found in milk and magnesia. Aluminum hydroxide is found in the antacid Maalox. Notice that your bases have OH a polyatomic ion, and it's that OH that's giving it the basic properties. Acids, most acids have a hydrogen written first. If it's an organic acid, usually the hydrogen is written last, but you will always have some sort of hydrogen if you have an acid. There are many acid-base theories. Let's talk about the most simple, and these are Arrhenius acids and bases. Arrhenius acids and bases release charged particles when dissolved in water. If it's an acid, it will produce hydrogen ion, and if it's a base, it will produce hydroxide ion. Adding HCl to water, I would get H plus and Cl minus. So this reaction is balanced for atom and also charge. So notice the +1 and the -1 on the right hand side, that they will cancel each other out, and so it will be neutral. Acid reactions also can be written with water added. And so what is happening here is we have this hydrogen ion is coming off and it's attaching itself to the water. So this H3O plus, this is hydronium ion. So when we're talking about acids, we are talking about hydrogen ions and hydronium ion. Essentially, the hydrogen ion is equal to the hydronium ion. When we look at our acid particle right over here, I drew out the Lewis dot structure. When this comes apart, the chlorine gets all those valence electrons, and so it ends up looking like this as far as its Lewis structure. The hydrogen ion just looks like this. Now, it doesn't have any electrons. So because it doesn't have any electrons, this H plus is often referred to as a proton, and it actually is a myth. So H plus is a myth. So it doesn't exist in nature in this form, in the H plus. So even though we're going to use it throughout this whole unit as an H plus, just know that it doesn't exist as a proton. Instead, what it does is it attaches itself to a water, and it exists as a hydronium ion. But to simplify things, we often just write it as an H plus, but just know in real life, it really attaches itself to a water. Now for a base, it falls apart just like a salt would. So it's going to make sodium ion in this case and hydroxide ion. Stop the video and see if you can classify each of these as acidic or basic. Here's the answers. So number 1, we see that OH, so it is a base. Number 2, we see an OH, and magnesium hydroxide has 2 OHs actually, and so it is also a base. We have hydrogen that is written first in number 3. This is an acid. And then on this next one, this is an organic acid, the COOH, and it's this H particle that comes off to form that acid. The last one, it's triprotic. That means it has 3 protons. When acids dissociate in solution, they will lose their hydrogen ions one at a time. So now the H2PO4 will go on and lose another hydrogen. And now the HPO4 minus 2 will go on and lose another hydrogen. So that's one thing to remember, that these hydrogens are lost one at a time. So even though there might be multiple hydrogen in the acid, it is done in a series of reactions. There are other acid and base systems. Let's look at this one. So it's found that NH3 or ammonia is found to be a base, and notice that there is no OH there. So how can it be a base? So we need a different classification system. These two men, Bronsted and Lowry, they independently came up with this acid and base theory, and they both said that acids are proton donors, so they will lose an H plus, and bases are proton acceptors, so they will gain an H plus. And you need to start out with a balanced equation. So let's look at this first one. I already told you that ammonia is a base. Let's see why it is. So we're going to look over to the other side of the equation and see what it did. So we see we went from NH3 to NH4 plus. So what it did is it gained an H plus. So that is gaining a proton. So therefore the NH3, because it gains a H plus, it is a base. Let's look at its neighbor and see what it does. So H2O becomes OH, and I see what it has done. It has lost an H plus. So this makes it an acid. Now notice that the double arrows, this is a reversible reaction. So let's look at the first thing there, NH4 plus, and let's classify it as an acid or base. So we're going to be working backwards. So we're going to be looking back, and I see that NH4 plus goes to NH3. So what happened to it? I found that it lost a proton, so this makes it an acid. To keep it a different acid from the acid on the left-hand side, we call it a conjugate acid. So now look what happens. Your base on the left-hand side becomes the conjugate acid. So that means, what does the acid become? It becomes the conjugate base. I see that when I go backwards, my OH minus, it gains an H plus, so that makes OH minus the conjugate base. And it's always this pattern. So if I can identify one component on the left-hand side, whether it's an acid or base, I can figure out the other three, because your acid always becomes your conjugate base. Right next to the acid will always be the base, and your base always becomes the conjugate acid. So let's look at this example down here below, our second one, and I see this COOH. So I know that this is an acid, and I can see it's an acid in this case because I see that's going to lose that H plus. So when an H plus goes away, then I get this right here. When I go backwards, I see that my CH3COO minus will gain that H plus, so that means this is my conjugate base. Next to my acid is my H2O, and this is acting as a base, and I can see it's acting as a base because it's gaining an H. And my base, when I go backwards, this is my conjugate acid. So whenever we have these Bronsted-Lowry acids and bases, they will typically be at equilibrium, and so you can go both directions. So your base becomes your conjugate acid becomes your conjugate base. Now notice I had water twice. So H2O there and H2O on the second example. The first example it's an acid, the second example it's a base. And this is called amphiprotic. So that means it can accept a proton, an H plus, or it can donate an H plus. Now you won't always have water in your reactions. This is just a transfer of the proton. And so whatever is accepting the proton is going to be your base. Whatever is donating the proton is going to be your acid. When you have a base, they typically have lone pairs that the hydrogen can attach to. And so let's look at my little Lewis structures up above. So I see right here my ammonia, my NH3, it has a lone pair. So when a hydrogen, an H plus, comes in, it just joins up right there where that lone pair is. And this ends up being ammonium. So NH4, and it has a +1 charge. And the same thing can happen to my water. So my hydrogen can join right here. And then this whole thing has a plus charge. So, and that is my hydronium right here. So we're adding the H plus. Make sure you add the H and you add the plus. Reactions between acids and bases always yield their conjugate bases and their conjugate acids. And later on in the unit, we're going to be talking about strength, but it's good to just start learning it now. Whenever you have a weak acid, its conjugate base will be stronger. So down here in this example, I have a lowercase a. Notice that it becomes an uppercase B. And what this means is that because the conjugate base is always stronger than a weaker acid, it will drive the reaction. So I can rewrite this little double arrow showing this. So I can see that a very strong reverse reaction, and then the forward reaction is not as strong. So a weak acid always becomes a stronger conjugate base, and vice versa. You can see here that I have a weak base, and notice that my conjugate acid is a lot stronger. And again, that encourages the reverse reaction to be favored more than the forward reaction. List the conjugate pairs for each equation. So I'm just going to pair them up, the acid with the conjugate base and the base with the conjugate acid. So this one is my base, and I see that this is my conjugate acid. because it gained that H plus. I add the H and I add the plus. And then my other one, so this one is my acid. It's going to donate the hydrogen ion, the H plus. So H plus is going to go away, so that leaves an I minus behind, and that is my conjugate base. And let's do this example down here. So this one is my acid, and this is my conjugate base. And this one is my base and my conjugate acid. So it's just kind of tearing it apart from that balanced equation. So we can see in this first example that we had an H plus go away. And in this next example, we had an H plus come in. The AP board really de-emphasizes naming in AP chemistry. And so on all of these examples, this is just to give you just a little taste of knowing some chemistry, knowing some naming, but just know you're not going to directly be asked for a name. On your homework, you can just look up any name that you need to, so you can use Google. Try to name it all by yourself, but then you can look it up. So this is a salt and bases naming review from the first unit. So whenever we have salts, we always name the metal, then we name the nonmetal or the polyatomic ion. So on this first one, this is sodium and it's chlorine, but I dropped the ending IDE. The next one, this is calcium. And there is no, anytime there's a metal, you don't use the Greek naming system. So there's no di, tri, or anything. This is just calcium chloride. On this next one, I can see I have a polyatomic ion. So I'm just going to name the polyatomic ion. So potassium nitrate. And the next one also has a polyatomic ion, magnesium nitrate. So those are our salts. Our salts have a metal and then a nonmetal. Now right here, here's our base because it has that hydroxide, and it's just named the same way because the OH, the hydroxide, is a polyatomic ion. So this would be potassium hydroxide. For your acids, you can use the polyatomic ions to help you name your acid. If you have a polyatomic ion that ends in ate, then it can become ic. And if it ends in ite, then your acid would be an us acid. And you want to add enough hydrogen ion to have a neutral molecule. So let's look at this first one. So I have sulfate. It has a -2 charge. So I know I can add 2 hydrogen ions. So I would be H2SO4, and that would make it neutral. And then I'm going to take the 8 and cross it out and put ic. So this is going to be sulfic, which sounds weird. So this is kind of an abnormal example. But I'm going to go back to the root word, which is sulfur, and I'm going to call it sulfuric. So sometimes you just have to say them out loud. This one, it ends in ite, so I'm going to cross out the ite and put us. And then again, add 2 hydrogens, so H2SO3. And this is sulfurous acid. So 8 to ic, ite to us. We use the polyatomic ions if there's oxygen in the acid. If it is just 2 elements and that H comes first, then we name it after hydrochloric acid. So the beginning is hydro, the ending is ic, and you can see the root word right there in the middle. So this next one is HBr. It's named just like the hydrochloric acid. So this is going to be hydro, but bromic acid. So this is what you do if there's just 2 elements. If there are 3 elements, then it's named after its polyatomic ion. So this is sulfate, and we just did this one. So this would be sulfuric acid, so 8 goes to ic. This is sulfurous acid. Now, selenium is in the same family as sulfur, and so because of that, it's going to have the same naming system. So even though I don't know about the selenite ion, it's going to act just like that sulfite ion. So this is going to be selenous acid. This is the polyatomic ion perchlorate. So perchlorate becomes perchloric acid. This is the polyatomic ion chlorate, so it's going to become chloric acid. There are 6 strong acids that you need to memorize: HI, HBr, HCl, HClO4, H2SO4, and HNO3. If you have anything else that's an acid and it's not one of these six, then it is a weak acid. There are hundreds of weak acids, so it is easier just to memorize the six strong ones. For the strong bases, there are also six of them. It is hydroxide that bonds with the alkali metals and the alkaline earth metals, so those first two metal families. So starting with the very first metal in the alkali metals, lithium hydroxide, sodium hydroxide, potassium hydroxide. The rest of the alkali metals with hydroxide would be strong, but they tend to be very reactive, so they're not very common in the laboratory. In the alkaline earth metals, the very first two alkaline earth metals are not strong when they're put with hydroxide. So beryllium hydroxide and magnesium hydroxide are not strong, but calcium, strontium, and barium do form hydroxides that are strong. The strength of the base increases as the atom gets larger, or it becomes less electronegative. What makes something strong? What makes something weak? What makes acids and bases strong is they have 100% dissociation. So for example, if I had hydrochloric acid and I start with 100 molecules of it, at the end, I'm not going to have any of those molecules left over. They will completely split up. And when they split up, I will have 100 molecules of the H plus and 100 molecules of the Cl minus. So I'm taking this molecule and I'm cutting it in half. So if I have 100 of them and I cut each of the 100 in half, I'm going to have half of the H plus and half of it will be Cl minus. So 100 and 100 of each. Now weak acids only partially dissociate and they will be at an equilibrium situation. So let's say for this acid, this is acetic acid or the acid that's found in vinegar. If I start with 100 molecules of it, at the end, let's say I have 95 molecules. That means I have a 5% dissociation. So I would have 5 of the H plus and 5 of this acetate conjugate base. Now, if you look at the equilibrium, it strongly favors the reverse reaction. So sometimes they draw these arrows with one that's longer than the other. And so for this one, because the reverse reaction is strongly favored, I would have a longer arrow going that way. This has a equilibrium constant that's going to be much less than 1, so it will favor the reactants. So in this upper right hand corner here is a picture, and it shows that in a strong acid, everything splits up, and these hydrogen ions, you don't see them as an H plus. Instead, remember that they grab onto a water and they become hydronium, so H3O plus. This second one, this one is a weak acid. And you see that the acid is mostly together. I only have one conjugate base and then one hydronium. And there's some other waters there too that have not reacted, but you can see that most of the acid stays together. Here's another picture that shows a strong acid and a weak acid. So when I look down here at this diagram, I see that I have chlorine and the hydronium. So what has happened here is our HCl, which is a strong acid, reacts with the water, and I get hydronium ion and chloride ion. And so the only thing I'm going to see are these two species, so just hydronium and just the chloride ion. In this next one, this is hydrofluoric acid, and it will dissociate in water and yield hydrogen ion and fluoride ion, but it only does it just a small amount. So they only represent one molecule that has separated. All of the rest of the hydrogen fluoride has stayed together. And then remember that hydrogen ion, it can grab onto a water. So you can write it this way like I just did, or you can stick water in there so you make a hydronium. Either one is accepted. So I actually prefer the first way because it's just less confusing. You don't have to remember to put the water in there, but know that either one is accepted, and this one is actually a myth. It doesn't really exist in nature. Remember, it does grab onto water. So the second one is probably more accurate, but either one is accepted on the AP exam. Some common weak acids and weak bases: hydrofluoric acid, which is used in glass etching. Phosphoric acid is used in soda pop. Acetic acid is the acid that's in vinegar. And then your weak bases: ammonia, NH3, that is a weak base. Anytime you have an amine, that will be a weak base. And this nitrogen, it has this lone pair of electrons. And so that means it is able to accept a hydrogen. So this hydrogen ion, it has a place to be. It will attach right there onto that N, and the whole molecule will gain the plus also. Down here, the last one is magnesium hydroxide. This is a weak base. Magnesium hydroxide you do find in some antacids. There's a relationship between acid strength and the acid equilibrium constant, or the Ka. The higher the number of the Ka, then the stronger the acid. If we have a strong acid, we are going to have a very large K. And in this slide, I just say it's large. It's going to strongly favor the product side, and that's because we have 100% dissociation. So technically, I don't have any of that acid left. And so when you go to do this K, you're essentially dividing by 0. So it's undefined. We just say it's large. It strongly favors the products. It goes to completion. There's another way to write it, our Ka. And that is if we have hydronium instead of the hydrogen ion. But either way, it's going to be large. Notice that these end up being the same thing, and that's because we don't put liquids in our equilibrium constant. Remember, products go on top, reactants go on the bottom. And anytime we have a strong acid, it's going to go to completion. We're essentially dividing by 0. It's going to be an undefined, very large number. The higher the Ka, the acid, then the stronger the acid. And remember the relationship between the acid and the conjugate base. If you have a very strong acid, you will have a weaker conjugate base. For weak acids, we are at equilibrium, so it is a reversible reaction, and it tends to favor the reactants, so I can have my unequal arrows there. And then I'm going to do it just like I have always done it. Products on the top, reactants on the bottom. So I have this hydrogen ion, and this is the acetate ion, and you will multiply their values by each other and then divide by the concentration of your weak acid. The weaker the acid, the stronger its conjugate base, and so therefore the conjugate base drives the reaction backwards. So that's why we have more reactants, because the conjugate base is stronger than the weak acid. The ranking of the acid and base strength has to do with the Ka for the acid or the Kb for the base. So here are just some common acids, and we can rank these from weakest to strongest. So my strongest one is going to have my highest number. So that's this first one. So this one would be the strongest. The weakest would be this 10 to the minus 10. And then the other ones are in between. So I'm going from weakest to strongest. So that one would be first, and then end with that top one. Acid and base strength. So strong acids completely dissociate in water, and so therefore their conjugate bases are quite weak. Weak acids only dissociate partially in water. Therefore, they're weak acids. They will have stronger conjugate bases. And in your book, they have this little picture that depicts water and the hydronium, and then I have water and the hydroxide. And so they just rank it. So you can see that the stronger the acid, then its conjugate base is weaker. So, and we can see this right here. These are strong acids here, and their conjugate bases are neutral or very, very weak. And so this chart just shows the trend.